the values what the propagation constant beta can assume. So we have seen that the value of beta should always lie between beta is the propagation constant of the mode that will be supported by the waveguide. So we have seen that this value of beta, which a mode can assume, should always lie between K0n and K0ng, where n is the refractive index of the cladding and ng is the refractive index of the core. So we arrived at this condition by invoking the values what kappa and gamma can assume. So we have seen that if kappa was imaginary, if kappa has to be imaginary, beta has to be greater than K0 into Ng. So if that condition was satisfied, if beta is greater than K0, if beta becomes greater than K0 into Ng, then then kappa becomes imaginary, and then you will be having an exponentially varying electric field for the mode inside the core. Whereas if gamma becomes imaginary, then you will see that Ey of x, which is the electric field profile inside the cladding, so that would become sinusoidal. So gamma is imaginary. So gamma can become imaginary if beta becomes greater than K0 into n. So realistically, so we don't want that to happen. So if gamma becomes imaginary, then Ey of x within the cladding would become sinusoidal. So those kind of modes where you have a sinusoidal profile in the cladding as well is what is called as the radiation modes. It's called as the radiation modes. So what we want in an optical waveguide, in an optical waveguide which can guide the signal from transmitter to receiver, is that you want a cosine or a sinusoidal profile inside the core and an exponentially decaying profile inside the cladding. So if that has to happen, gamma should be always real. So gamma should be real, kappa should also be real. But on the other hand, if gamma becomes imaginary, then you would see that when gamma becomes imaginary, so inside the cladding we had assumed an electric field profile of the form e raised to minus gamma x. So if gamma becomes imaginary, then this term is going to become, so you would see that the solution of Ey of x inside the cladding would become sinusoidal rather than exponentially decaying profile. It would become sinusoidal. So that means that you can have a mode that exists inside both the claddings and you call those modes as the radiation modes. In fact, radiation modes cannot propagate. It just gets radiated, but it cannot radiate over a large distance. So note that the distance between the transmitter and the receiver is usually very large. So radiation modes cannot really propagate. It can just radiate and then it will die off very soon. So those kind of modes are called as radiation modes. And we have seen that given these two conditions, so we have seen that K0 into n should be less than beta, should be always less than K0 into Ng, where Ng is the refractive index of the core and n is the refractive index of the cladding. So if I divide throughout by K0, I would get n, which is the cladding index, should be less than beta by K0, should be less than the guide index. And this parameter, beta by K0, is what is called as the effective index of the mode or the effective refractive index of the mode. Effective refractive index of the mode. And it's denoted by n effective. So the effective index that is seen by the mode would be always lying between the cladding refractive index and the core refractive index. It should never exceed or should never go below these two values. It should be always be lying between the cladding refractive index and the core refractive index. So note that the n effective or the effective refractive index should always lie between these two values, but it's never the average of these two. It should be always between the cladding refractive index and the core refractive index. So any mode that will be guided by the waveguide would be having a effective refractive index that always lies between the cladding refractive index and the core refractive index. So this is what you call as this is what is called as the effective refractive index or N effective. So it's a very important parameter for an optical mode. So this is where we have stopped in the previous class. Okay. Now we would like to examine whether in our one of our previous lecture we had seen that uh, if 0 less than v by 2 less than pi by 2, so 0 less than v by 2 less than pi by 2. So, or in other words, if 0 or 0 less than v less than pi. So note that on the y-axis we are plotting v by 2, on the x-axis we are plotting capital K. And this v number is the one which is going to decide the number of modes that will be supported by the waveguide. How many modes can be supported by the waveguide is decided by this v number. And you know what is v? V is given by k naught into d into root of n n core square minus n clad square. So this number is denoted by the V number, and if half of this V number is less than pi by 2, that means our circle. So this would be the circle. So you would see that this circle cuts the k tan k curve only once. So which means that physically what it means is the waveguide is going to support only one mode. So this was the curve. So in fact this circular curve, so this was for the TE mode. In the case of a TE mode, the equation was k tan k into root of v by 2 the whole square minus k square. Whereas in the case of TM mode, the equation was slightly different. In the case of TM mode, the equation was k cot k is equal to k cot k is equal to minus of ng minus ng by n the whole square into root of v by 2 the whole square minus k square. So this is the eigenvalue equation for the TM mode. So for the TE mode, this is the equation. So you see that in the case of TE mode, you are going to have a circle. Whereas in the case of TM mode, because of this term, this ng by n the whole square, where ng is the core refractive index and n is the cladding refractive index, because of this scaling factor, this curve, what you are going to draw is no more a circle, rather it's going to be an ellipse. So it's going to be an ellipse. So that equation, so this is the circle. So this one. So this one is a circle. So this k tan k is equal to root of v by 2 the whole square minus k square, and the other one is for the is actually for the it's actually for the TM modes, because of the presence of ng by n the whole square into root of v by 2 the whole square minus k square. So this ellipse what you see, so this curve, so this is an ellipse. So that's an ellipse. So that is for the TM modes. Let's say it's for the symmetric TM mode. So this is for the symmetric TE mode. This is for the symmetric TM modes. And again, you would see that you would see that the curve has cut the curve has cut this curve only just once. It is cut only once.
Sir?
Yeah.
Sir, in last class, I think you said that both will be ellipse for TE and TM mode.
Can you be louder, please?
Sir, we have a class now, sir.
Yes, there will be class now.
Yeah, okay, then we'll continue this in the next class. So we'll continue about this in the next in tomorrow's class. Okay, I'll stop here.